Hello dear friends, welcome back to MACSGATE. We are learning Python programming. Under Python programming, we are talking about operators. So let us see the third part of operators or Python operators. And in today's session, we mainly talk about this bitwise operators, followed by some special operators like identity operator, membership operator, which concludes all the operators. Then we try to see the precedence of operators. Okay, so that is the idea or agenda for today's session. So let us start with bitwise operators. See, the bitwise operators are used to perform operations on binary representation of integers. Okay, so the operands for bitwise operators must be of any integer type. Okay, you can use integer or bool. Bool also can be converted to integer type because of that. Okay, so we can only apply this bitwise operators on integer type. Okay, so they are not actually applied on the integer representation, they are applied on their binary representation. That is binary representation of the given integers. These bitwise operators are applied. These operators works on the individual bits of the integers rather than on the integer as a whole. So they are not applied on integer as a whole, but they are applied on the bits, individual bits. Okay, so it is a little interesting story. So we'll try to understand with examples also. The first one is bitwise AND operator. Bitwise AND operator. See, the output of bitwise AND is 1 only when the corresponding bits of the two operands is 1. So what I do is I'll just take a simple example to explain this bitwise AND operator. And this is the symbol used for bitwise AND operator, my dear friends. Suppose you are having a integer, but ultimately we are going to work with their binary representations, and luckily using 0b we can get the binary representation directly, so that we can understand this bitwise operations very clearly, my dear friends. Okay, suppose you are having a binary representation, say 0 1 1 0 1 0 0. Okay, I am just using say 8-bit number, but here in Python it's not restricted to 8-bit or 16-bit, sir. So this particular thing happens based on the precision happens on a go. Okay, so it won't be fixed to 32 bits or 62 bits. Am I clear? We'll try to understand that. Now suppose this is your first integer or the binary representation of the first integer. Let us take the second integer, say 1 0 1 1 0 1 1 0. Now when you do the bitwise AND operator, so this bitwise AND operator gives 1 when both the bits are 1. That is, the story is very simple, sir. Suppose the bits are say 1 1, the bitwise AND operator will give you 1. In remaining or in the remaining cases, like when you have 1 0 or 0 1 or 0 0, the result would be 0, my dear friend. So here this is applied on the bitwise or bits. So here you see 1 0, because both are not 1, you are going to get 0. 0 1 also you get 0. 0 1 it is 0. 1 0 it is 0. 0 1 also it is 0. But now you see 1 1. At this position you get 1. 1 0 it is 0. 0 1 it is 0. So this is the result, my dear friends. Okay. So if you want, you can verify this. And if you want to know what is this number, also you can verify. See, this number, when you have a binary representation, you can get the decimal equivalent of this. This is 1, 2, 2 square, 2 cube, that is 8. This is 16, 32, 64. 64 plus 32 plus 8 plus 1, that is 40, 104, 105. So this is actually 105. And what about this? Okay, it is like, like 1, 2, 4. So you are having 2, 4, then 8 is missing, 16, 32, 64 is missing, then 128. So this is the number. So 10, 20, 22. So this is 2 plus 3, 5, 6, 8, 182. Please verify that, sir. I am assuming 105 and 182. So you are going to get what result? Let us verify this. Okay, 105 and 182. So what is the result? Let us see the bitwise AND operation. So it is giving result 32. You can check this result: 1, 2, 4, 8, 16, 32. So the result is 32, my dear friends. So it is very, very easy for you to understand this. Am I clear? And luckily in Python we are having binary representation directly we can use. For example, if you have any numbers, directly you can use the binary representation to understand this bitwise operators perfectly. You can just take any number, sir. It's not necessary that you need to take 8-bit number. Am I clear? So it automatically tries to identify the number or identify number of bits. Okay, so let us try to see this. 0B 0011. So what is the result? So here what happened? First digit 10. So they are different, so you are not going to get 1. Again, next place, if you see 10, they are different. 11. So only if you see the unit tens, you say units twos position, there is a matching 11. So the answer is 2 for this. Of course, even though you return the binary representation, the result won't be in the binary format, sir. You get the decimal answer. If you want the binary answer, you can use the bin function, which can convert the number into binary format. So this is the answer. If you observe, it is not showing the 4-digit number, okay, or 4 bits. It is just showing that required precision only. Okay, always it show you the required precision only in Python. Is that clear? Please note. So this is bitwise AND operator, my dear friends. The next one is bitwise OR operator. See, the output of bitwise OR is 0 only when the corresponding bits of 2 operands is 0. Okay, so let us try to understand bitwise OR operator. The bitwise OR operator. So it is denoted by the pipe, single pipe symbol. Okay, if you have any doubts, you can ask me, my dear friends. So here, for example, if you are having 2 numbers, let us say the 2 numbers in their binary format are, say, 1 0 1 0. I am taking just number with only 4 bits. Am I clear? Just for understanding purpose. After understanding, you can take 8 bits or 88 bits also, it does not matter. Next one is, say, 1 1 0 1. Now I want to use bitwise OR operator. You see, it is 0 only when both are 0. Otherwise, you are going to get the result equal to 1. So both are 1, you get 1. One of them is 1, then still you get 1. One of them is 1, still you get 1. One of them is 1, still you get 1. So the result for this is 1 1 1 1. Actually, if you see the binary representation of it, what is the number? 1 0 1 0. It is 1s, 2s, 4s and 8. 8 plus 2, this is actually 10. And what about this? It's like 8 plus 4, 12 plus 1, 13. This is actually 13. And what is the result here? The result is actually we are having 8 plus 4, 12 plus 2, 14 plus 1, 15 is the answer. Okay, you can just verify 10 or 13. Let us verify that. What is 10 or 13? So that is the result. 15 is the result. You can try this, sir. You can try this like 0B. You can have a maybe 8-bit number or 8-bit number or 32-bit number also you can take. It does not matter. Okay. So let us try 0 1 1 1 0 1 0 0 1. So okay, let us try different. This one is like we are having 4 plus 4 9-bit number I taken. This time I take only 3-bit number. So automatically what happened? The left side's bits are filled with zeros. That is obviously what happens. So what is the result, my dear friends? You can check 237. So what is happening? This is 0 because the corresponding bit is 0 here for the second number. This is 1 because one of the number is 1. Even though the corresponding bit in the second number is 0, the result is 1. So what is the result we are going to get here, sir? The result which you are going to get is 0. The next one is 1. Next one is 1. Next one is 1. Next one is 0 0. Next one is 1. Now 3 bits and 3 bits. 0 1 you get 1. 0 0 you get 0, the last one 1 0 you get 1. So this is the number set. So the corresponding decimal form is 237. You can easily verify this set. Here it is 1, it is 2, it is 4, 8, 32, 64, 128. So you can just add them to get the required answer. 128 plus 64 plus 32, 16 is missing, plus 8 plus 4, 2 is missing, plus 1. So you can simplify to get the required answer, my dear friends. So this is your required answer. The next one is bitwise XOR, exclusive OR. So XOR will be true if at least one, any one of them is true. Okay, if both are true, then it is false. That is, if both are 1, then it is 0. If both are 0 also, then it is 0. If any one of them is 1, then only the result is 1. So the output of bitwise XOR is 1 only when the corresponding bits of the two operands are opposite. So if you get 1 0, you get 1. If you get 0 1, you get 1. Otherwise, always the result is 0. So let us try to understand this bitwise XOR with example. Bitwise XOR. You can take the previous example also, like 1 0 1 0, 1 1 0 1. Now here what happens? There is a matching, so the answer is 0. 0 1 not matching, you get 1. 1 0 not matching, you get 1. 0 1 not matching, you get 1. So the required answer here is, 1 2 4. That is 4 plus 2 6, 6 plus 1 7 is the answer. So you can take 10 13 XOR and let us see what is the required answer. What is XOR of 10 and 13? 10 XOR 13. So what is the answer? 7 is the answer, my dear friends. Actually, for this, bitwise operators, there is a order of precedence. Okay, so please note this order of precedence for bitwise XOR, my dear friends. Bitwise operators. So the order of precedence is like this. AND is having higher precedence, then XOR, then OR. So this is the order of precedence of bitwise operators. AND is having higher precedence, then XOR, then OR. OR is having lower precedence. So sometimes people feel that they are all having equal precedence. It is not like that. So let me take some simple example like 10, 13 and 14. Let us take these three numbers and I just want to do this AND OR operations in different order. Let us see what happens. So let me take the numbers like this. 10 means what, sir? 1 0 1 0. I want to do XOR. 13 means 1 1 0 1. Then I want to do AND operation. Then 14 means what, sir? This is 15, na? This is 1 1 1, 0 is 14. So now I want to see what is the result. So here AND is having higher precedence. So first this will happen. Finally this operation will happen. That is, first bitwise AND operation between these two numbers will happen. That is 1 1 0 1, 1 1 1 0 will happen. What is the result? This is 0, this is 0 because AND operation 1 1. So the result here is 1 1 0 0. Then XOR operation with this. That is 1 0 1 0. That is 1 0 1 0 XOR with 1 1 0 0. Here we are doing XOR. XOR will give you 1 if both are opposite values. So here it is 0, opposite therefore 1, opposite therefore 1, same therefore 0. So what is the answer? 0 1 1 0 is the answer. That is 6 is the answer for this. So let us check this. 10 13 14. Let us check this. 10 XOR 13 and 14. So what is the expected result, Babu? The expected result is 6. Suppose first this happens, then AND operation happens. In that case, what happens? Let us check. 1 0, because the order of precedence is important. Na? Suppose first this happens, 1 0 1 0, 1 1 0 1 XOR is happening. XOR means this is 0, this is 1, this is 1, this is 1. Then AND operation with this, that is 1 1 1 0. So what is the result here? 0 1 1 0. Luckily here in this case, okay, the answer is different. Huh? Okay, same answer you're getting, but it is not always the case, my dear friends. Okay, it is not always the case. You can verify different examples. Okay, If you want, I can take some more example. You can try different examples. See, the idea is first you do XOR, then you do AND. The answer will not be the same. So the order of precedence is very, very important. You can try different examples like 0 0 1 1 1 1 0 0. Okay. Now if you do XOR first if you do XOR first, you get 1 1 1 1. Okay. Then if you do AND operation, you are going to get 0 0 0. Okay, it is happening same, but generally it is not the case, my dear friends. Maybe I am not finding the suitable example, but the order of precedence matters. Am I clear? Please note that order of precedence matters. You can try different examples, Babu. Okay, you have this, okay, interpreter, use different examples and try what is the different answer. But if you want that order of precedence to be the way you want, you can use parenthesis. That is, first you want to do XOR, then followed by AND, use the parenthesis, my dear friends. Am I clear? That is idea. So that is about bitwise AND bitwise OR and bitwise XOR. Out of these three, bitwise AND is having higher precedence than XOR, then OR. Now comes bitwise complement. So this bitwise complement generally troubles, but in Python, because you can visualize the numbers very clearly, so it is very simple for us. So let us try to understand this bitwise complement. See, the bitwise complement operator is an unary operator. Unary, it applies only on a single operand, and that single operand must be integer. Okay, so bitwise complement operator flips the bits of the binary representation of the integer, changing ones to zeros and zeros to 1. Okay, see, here there is one very interesting story which we need to understand properly, my dear friends. If you understand that, then generally this bitwise complement does not trouble you. The result depends on how integers are represented internally, so which typically varies based on the system's architecture. But in Python, as I mentioned, integers are internally represented with arbitrary precision, meaning that the number of bits used to represent an integer is not fixed to 32 or 64 bits. See, actually this bitwise complement depends on how many bits are used to represent a particular integer. But in Python, integers are internally represented with arbitrary precision. It is not fixed to 32 bits or 64 bits, my dear friends. So depending on the number, the precision will change. Am I clear? But this bitwise complement depends on that particular architecture. Okay, so how it works, let us try to understand with examples. And please note, positive numbers are represented directly in the memory. That is, their binary representation is directly, that is, if it is a by a positive number, directly take the binary representation, and it is that binary representation is directly stored in the memory. Whereas if it is a negative number, its 2's complement representation is stored in the memory. See, this point is very, very important, my dear friends. I just want you to understand with one simple example here. For example, suppose you are having number 4, sir. You are having number 4 which is positive. So in the memory, how it is represented, sir? In the memory, how it is represented? 1 0 0 it is representation. And suppose if it is a 4-bit number, the leading fellow will be 0. If it is a 5-bit number, the leading bit will be 0. Actually, what happens for positive and negative, the the most significant bit or the leading bit decide this sign. Am I clear? So whenever it is positive, the most significant bit will be 0 only. So this is how it is represented in the memory, my dear friends. Okay, in Python you will just see 1 0 0, but generally in other system or in other programming languages, the size of integer is fixed, like 2 bytes or 4 bytes. Depending on that 32 bits are filled. Am I clear? This 1 0 0 is fixed, and to the left of that you will get all zeros when it is a positive number. So this is how it is represented in the memory. Positive numbers are directly represented in the memory as it is. But if it is -4, what is -4, my dear friends? See, -4 means what? Here the leading bit would be, the leading sign bit would be what? +1. So here you may be having some zeros. Let me take 8-bit number. So it is 4 + 4. So this is how it is represented. So this leading bit is, one second, let me make it equal, number of bits, like 4 plus 4. So the leading bit, actually we call it as MSB, most significant bit, most significant digit or most significant bit. This is 0 means it is positive. If this is 1 means it is negative. See, whenever it is a negative number, okay, I think one second, there is a problem with audio and video. Let me relaunch the video. Just give me 1 minute. Sorry for that. There was a problem with the video due to the power failure. So let us continue. So the most significant bit or the leading bit, if it is 0, then it is positive. So 0 means positive. So minus 4 means, so same 4 only. The most significant bit will be 1, the remaining fellows 0. So this will tell you it is negative number. But in the memory, this negative numbers are stored in 2's complement. That is, actually the 2's complement of this number is stored in the memory. The 2's complement is stored in the memory. So what is 2's complement of this number, my dear friends? So the leading bit will remain, that shows the sign. Now the remaining, like whatever number you are having, you take 1's complement, that is zeros change it to 1, 1's change it to 0. So all these zeros are changed to 1 and 1 is changed to 0. Then add 1 to it. So 1 plus 1, don't say 2, it is binary addition. 1 plus 1 is 1, 0. So 1 is the carry, you get 0, 1, 0. Now 1 plus 1, 1, 0. You carry, you get 1. So this is how it is represented in the memory, my dear friends. Of course, it is not shown. When you write minus number, same thing will be shown when you print it. But in the memory, this is how it is stored. Okay. Stored in the memory like this. Stored in memory. This is what is stored in the memory. Now, for this number, when you take complement. So now what happens when you take complement of 4, what happens? When you take complement of 4, what happens? So complement, what it will do, it will convert 1's to 0's and 0's to 1's. 1's are converted to 0's and 0's are converted to 1's. So this 0 will be converted to 1. All these fellows are converted to 1. That is 1, 1, 1, 1, 1, 5 1's, then followed by 0, 1, 1. But because it is negative number, okay, because it is negative number, the 2's complement of this is your answer. So what is the answer, my dear friends? Second, is it continuing or is it done? Yeah, it is continuing, right? Is the video continuing? Yeah, it is continuing. Yeah. What has happened, sir? Why it is showing it is done? The live is still on, right? The live is still on. Yeah. Sorry, very, very sorry, because there it is misbehaving with me. Sorry for that. Okay. So now what happens? The 2's complement of this is the answer. The 2's complement of this will be the answer, my dear friends. Okay, actually this is how it is stored, but the 2's complement is what is your output answer, my dear friend. The 2's complement is what is your output. Please note that. And for that we are having totally 3 methods. To find this 2's complement, there are 3 methods totally. I'll give you the 3 methods. Okay, I'll give you the 3 methods. So what is the output, we'll try to understand. But when it is a negative number, see, for positive I told you, for when it is a negative number, it is already stored like this in the memory. And when you take complement of this negative number, when you take complement of this negative number, so directly what happens? Complement of this is your answer. What is complement of this? 1 is changed to 0, 0, 0, 0. That is all these 6 ones are zeros. Then this zeros convert to 1. And because we are having leading 0, that is direct answer. So this is your answer. And what is the answer for this, my dear friends? 3 is the answer for this. So when it is a negative number, internally it is stored as a 2's complement number. And when you take complement, your answer is straightforward. Answer is straightforward. So here internal work is more, but the complement work is very less. Internal work is internally how it is stored, that work is more, but the complement work is very, very simple. Once you know this internal storage, the complement of that is just change ones to zeros and zeros to ones, you get the required answer. But here, when you are having positive number, after taking the complement, you are getting the internal storage. But that particular storage, how you get the answer? You need to take the 2's complement of that. That is your required answer, my dear friends. Okay, so let us understand what is the answer for this. For that, we are having 3 methods. So let me explain the 3 methods to you. Let me explain the 3 methods. So when you are having number 4, I am assuming 8-bit number. I am assuming 8-bit number. So it is like 1, 0, 0, the leading zeros. Now when you take complement of this, what happens? This is 1, 1, 1, 1, 1, 0, 1, 1. Now the 2's complement of this is your answer. 2's complement is the answer. See, actually, this is the internal representation. The memory representation, you got it. But that you need to convert. The 2's complement of that is your answer. Is answer. And how to find 2's complement of this? There are 3 methods. Method 1. Method 1. See, in the method 1, what we need to do is, okay, you keep the leading fellow as it is, you write 2's complement of this. So how to find 2's complement of that? The sign bit you keep as it is, remaining you convert zeros to ones and ones to zeros. That is, remaining fellows you convert zeros to ones and ones to zeros. So you get 0, 0, 0, 0, 1, 0, 0. After converting, that is, after taking 1's complement, you take plus 1. You add 1 to it. So what happens? 0 plus 1 is 1, 0, 1. This 0, 0, 0, 0, 1. See, actually this 1 is sign bit. So this is your answer. And because you are having sign bit 1 means it is a negative number. So the answer is minus, what is this number? 5. Minus 5 is the answer. Minus 5 is the answer. That is method 1. Now let me tell you method 2. Let me tell you method 2. See, method 2 directly, it is like manually whenever you are doing, you can use method 2 or method 3, my dear friends. But internally, if you want to understand, you need to take this. Because the 2's complement, how to find it, sir? How to find 2's complement? Take 1's complement, then add 1 to it. That is how we get 2's complement. The method 2, what we do is directly this representation you take it. In this, you find the positions of zeros. Where is 0? You try to identify. So it is like, this position is 1, this is 2's position, this is 2 square position, this is 2 cube position, this is 2 power 4 position, 2 power 5, 2 power 6, 2 power 7 position. So this 0 position is 2 square position. So what you do, you take 2 square but with a minus sign. Wherever zeros are there, the corresponding numbers you take it, okay, with a minus sign. And because there is only 1 0, we are very lucky, then you just subtract 1, and this is your answer. Minus 5 is the answer. This is manually when you are doing finding complement. This is how we can do it. Now let us see the method 3. Now let us see the method 3. Let us try to understand method 3. See, method 3, what we do, directly take the given number. Directly take the given number. Am I clear? Then what we need to do is, you convert zeros to ones, ones to zeros. Okay. Oh, sorry. Directly you take the given number, that is 0, 0. Okay. 0, 0, 0, 1, 0, 0. Okay. What you do is, you just add 1. And whatever answer you get, for that you just take minus. For that you take minus. So what is it? It is 1, 0, 1, remaining all zeros. See, minus means you can represent it as minus means leading MSB, you can make it 1, or you can just write down this, whatever this number is there, minus of that is your answer. So what is the answer, sir? Minus 5 is the answer. Minus 5 is the answer. Okay. Of course, I given so much story to you, but I'll give you a simple technique in Python, because the integer number is having arbitrary precision. Generally what answer you get, I can directly tell you, my dear friends. In Python, what is the answer, I can directly tell you. Let us try to understand. So whenever it is 4, whenever you find a number, okay, you just take this number 4. On the real line you take it. What is one number more than that? 5. When it is plus or minus, whatever number is given, if you want to find binary, bitwise complement of that particular number, one number more than that with a minus sign. For example, if you are having 12, what is bitwise complement of 12? One number more than that with a minus sign. With a minus sign. You take 148. What is complement of 148? One number more than that with a minus sign. It works. You can verify this. Of course, I given the method, 3 methods I given. You can check any of the 3 methods. With that, I can tell you this answer. But here, because we are having arbitrary precision, because the number of bits are not fixed, so there is no problem with overflow conditions. Am I clear? So we are very, very happy with this, my dear friends. And what about negative number? What if I am having negative numbers? What if I have negative numbers? So if you are having negative numbers, let us say minus 5. So on the real line, you write down minus 5. What is one more than that? Minus 4. See, negative number, one more than that, don't say minus 6. One more than minus 5 is minus 4. So what is the complement of minus 5, sir? One more than that is minus 4. Minus of that, that is plus 4 is the answer. Please remember this. Suppose if you are having minus 112, what is complement of minus 112? What is complement of minus 112? Let me rewrite this. What is complement of minus 112? One more than this is 111. That is the answer. You can take any number, sir, because of arbitrary precision, this always happens. Suppose if it is a fixed bit number, then we need to worry about the overflow conditions and all, but here we are lucky. So in Python, happily you get the required answers very quickly, my dear friends. Okay, but the story we need to understand, so I am just giving you the stories. Sorry for that. Is that clear? So let us take problems here. I think it is markdown cell, so let me take code cell. So now, as I told you, what is bitwise complement of 4? We just now seen minus 5. You can take bitwise complement of 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Any big number you take it. Okay. Still you get the answer one more than that. So if it is 9, 91. I am just talking about last 2 digits. I am not reading the entire number. 91, but with a minus sign. So same number with one more than, that is this number plus 1 with a minus sign. That is, if you are having n, minus of n plus 1 is the answer. So that is the answer. You take any big number, it works in Python. Now what about negative number? Suppose if you take -4. So what is 1 more than -4? -3. Minus of that is 3 is the answer. So when it is minus number, see always 1 more than that. Minus of that is your answer. Minus of that is your answer. You take any big number, sir. Okay. So 1 more than that is 788. Okay. Oh, sorry. Is there any? Okay. You have to take, bitwise complement. Na? If you write the same number you are going to get. You are here also. I need to take, complement. What is complement of this? Complement will be minus of -3 plus 3. So minus of that 788 is the answer. You can try any number of examples like this. Is that clear? So that is about complement, my friends. Then comes shift operators. Even shift operators are binary operators only. Shift operators are binary operators only. Okay. The shift operators move bits to the right or left. The bits are moved either right or left, my dear friend, depending on whether it is left shift. If it is left shift, bits are moved to the left. If it is right shift, bits are moved to the right. Okay. So let us see what is this right shift operator. The right shift operator. See, the right shift operator shift all bits towards right by a certain number of specified bits. So here this is how we represent it, sir. The number, integer number generally, or directly you can write the binary format of the number, and you are having two greater than symbols, that is right shift operators. I means specified number of bits. So whenever you give the number and specified number of bits, the result when the bits in A are shifted right by I places. So the left hand side vacant cell are filled with sign bit. That is, if it is a positive number, they are filled with 0. If it is a negative number, they are filled with 1. So that is what happens, my dear friends. But as I told you, Python is having arbitrary precision. Generally, you may not able to identify this, my dear friends. So let me just show you. Suppose you are having a number, say 101101. Now I want to shift right by 2 bits, or let me first shift it by 1 bit. So when you shift it by 1 bit, what happen? This will move to right, means that bit is gone. So we are only going to get this answer, my dear friends. So what is the expected answer, my dear friends? What is the expected answer? 10110. Actually, the leftmost bit, depending on, because it's a positive number, the leftmost bit must be filled with 10, because when you move one bit to the right, one position is filled with 0. One left position is filled with 0. But here in Python, you will not see, sir. You only see this answer. Let us see this. Oh, now you might be getting, what is this? I am getting 22. But I said this is the answer. Actually, it is the binary representation. So you just see this like, bin. Bin of that you see, then you will understand what is that answer equal to. You can see 10110. This is the answer. Okay, 22 is the decimal equivalent of that. Decimal equivalent of that number. Hope you understand. So whenever you do right shift, that is what exactly happens. Now, can you tell me what is this number actually? Okay, let me have this. What is this number actually? This number is 45. Okay, now you just divide it by, okay, I do integer division. You just divide it by 2 and tell me what is the answer. 22. And you see the answer here. Let me remove this bin and check this. What is this answer? 22. Okay, let me move it to the right by 2 bits. What is the answer? 11. So you moved it to the right by 2 bits now. So you you divide it by 2 square. See, when you move right by 1 bit, you do the floor division by 2 power 1. When you move right by 2 bits, you do the floor division by 2 square and see what happens. And you see the same answer. So the right shift is equivalent to right shift by I bits is equivalent to floor division by 2 power I. Right shift by I bits is equivalent to floor division by 2 power I. Please note that. Now let us see the left shift operator. So the left shift operator shift all bits towards left by certain number of specified bits. So when you are having a left shift I is the result when bits in A are shifted left by I places, the right hand side vacant bits are all filled with 0. Here right hand side vacant bits are filled with 0. You will see this. This right hand side vacant bits will see clearly, my dear friends. Okay. So let us try to understand. Suppose I am having 0, 1, 0, 1, 1 and I want to left shift by 1 bit. So when you left shift by 1 bit, what happens, sir? So this is moved left by 1 bit. This is moved left by 1 bit. See, actually, when you move left by 1 bit, what happens? The right position, one vacant position will be there, that will be filled with 0. So the required answer would be, 1, 0, 1, 1, 0. Actually, if you see the binary representation of it, then you will understand the correct answer, my dear friends. See the binary representation of that, that would be the answer. Okay. So let us see what is the answer. You can see 1, 0, 1, 1, 0. Okay. And if you move by 2 bits, you get one more 0 here. You move by 3 bits, you get one more 0. See, normally in other programming languages, the number of bits for representing an integer is fixed, but here it is arbitrary precision. Okay. It can take a very large numbers also. Okay, so there won't be any restriction, my dear friends. So this is the answer. But what I want you to understand is, what is this original number 1011? It is like 8 plus 2, 10, 11. It is originally 11. Okay, so let me take this. Sorry, 1011. Now what I do is, okay, first let us start from here. We move only 1 bit. This is the answer. Okay. Now here you multiply by 2 and see what is the answer. Even for this I will see the binary representation. I will see the binary representation. And you see the answer is exactly same. Now you move left by 2 bits, you multiply by 2 square. See what is the answer. See what is the answer. That is, moving left by I bits is equivalent to multiplying the number by 2 power I. Multiplying the number by 2 power I. That is the idea, my dear friends. Please note that. You can do anything, sir. Suppose if you want 5 bits, you can do raise it to the power 2 power 5. So what is this answer and what is this answer? They are one and the same. So that is the idea here, sir. Right shift and left shift results. So a right shift to I bits is equivalent to floor division of a by 2 power I. And left shift of a by I bits equivalent to a multiplied with 2 power I. So that is the idea, my dear friends. So that is about your shift operators. Am I clear? Hope you understand. Okay. And you already seen this, right shift, left shift operators. We also seen, bitwise AND, bitwise OR, bitwise XOR operators. So we can also do these operations using, compound assignment. Just like how you do compound addition, compound multiplication, similar way you can also do this compound assignment operation with this bitwise operators also, except not cannot be done, sir, because that is unary operator. Am I clear? So Python also support for analogous bitwise assignment operators such as AND equal, that is bitwise AND equal, bitwise OR equal, bitwise XOR equal, bitwise left shift equal, bitwise right shift equals, which allow you to perform bitwise operation and assignment in single statement. Okay, you can do that. For example, you can just check this. So for example, if you are having 23 and is equal to, okay, oh sorry, you want to do bitwise AND operation, no? So it is like 23 and something. Okay, generally you cannot do it for number. Now how can you assign to this? Okay, let me take a is equal to 23, okay, and b is equal to 34. Now I can do a bitwise AND is equal to b. I can do this. Please note that. So what is actually doing its what actually happening here, sir? We are actually doing a is equal to a bitwise and b. So a bitwise and b, that result is assigned to a. Am I clear? That result is assigned to a. So if you want, you can just see the binary representations, then you can easily understand this, my dear friends. Okay. So 23, what is binary representation of 23? Let us see. Bin 23. and bin 23. Bin 23 is what? 10111. So this is 23. Then again go back to this. What is binary representation of 34? This is 10010. Let us go back here. Okay, think we should use same number, 10010, right? Okay, so don't worry if you are not having, you know, matching number. Don't keep zeros right side. You can keep zeros left side, sir. You can keep as many zeros on left side as possible. Now what about the bitwise AND operation between them? Bitwise AND operation between them. So here 0 1 is 0, 1 0 is 0, 0 0 is 0, 1 0 is 0, 1 1 is 1, 1 0 is 0. So answer should be 2, my dear friends. So actually initially A is referencing to the object 23, B is referencing to the object 34. Now when you do A is equal to A bitwise and B, now the result of A is 2, that is A now reference to the object 2. See, 23 object remains same, but A now reference to the object 2. This is what actually happens. Hope you understand. Is the idea clear? Clear? Right. Good. So let us go back to this and run this. See the output. So what is the output, sir? Of course, we not printed here, no? So if you print here, then you know the output, my dear friends. So what is A value? A is 2. You want, you can see the binary representation of that. You only get 1 0 for that. So that is about bitwise operators, my dear friends. Okay, very good. Now we are left with 2 more operators. One is identity operator, the other one is membership operator. These are the special operators which are very, very useful, especially with, control flow structures. Generally with control flow, these are very, very famous and very, very useful, my dear friends. The first one is identity operator. See, identity operator is used to compare the memory addresses of 2 objects to determine if they are same objects or not. Okay, so I want you to understand. Okay, maybe this. Okay, I want you to understand. See, suppose A is equal to 10. What does it mean, sir? A is referring to the object 10. Now, when you say B is equal to 10, I told you from 0 to 256, they refer to the same object. So let us take big numbers so that this will not trouble us. Okay, luckily it may happen. So let me take 1000. A is equal to 1000. That is, A is referring to the object 1000. B is 1000. That is, B is referring to a different object whose value is also 1000. That is, this is a different memory address. Now if you say A is B, there is an operator called identity operator. A is B, that is whether their ID of A equal to. So what does it mean, sir? Actually A is B means, what is the meaning of it? Whether ID of A, address of A is equal to ID of B. This is what you are verifying. This means this. You are checking whether they are having same ID or not. So obviously this will give you the answer false, because they are 2 different objects, they are not same object. See, if their IDs are same means what, sir? They are same object. Now look at this. I say C is equal to A. What does it mean? So we are having a reference C or a variable C which also refers to A. Now if I say C is A, the result will be true, because both are referring to the same object. That is, AC means the same object. They are same object. So this is used for that particular purpose, whether these 2 objects are same objects or not. That is, they refer to the same, these 2 variables refer to the same object or not. This is very, very important, my dear friends. And what about the other one? Is not. So if I say A is not B, that is correct, because A, B are referring to the different object. This will be true. This is just reverse of this side. they are same object. Is means they are same object. Is not means they are not same object. They are different objects. That is it. So let us try to see this. So here is returns true if the operands are same object. Same object means they refer, the variables refers to the same memory location or same object, and false otherwise. And is not returns true if the operands are not the same object. False otherwise. That is the story. And please note this, my dear friends. We use equal to for content comparison. Content comparison, we are going to use equal to. Okay, that is to check if the objects have same value or not. Okay, only content is same, but the objects may be different. And is operator is used for address comparison. That is, they are same objects or not. See whether their values are same or not. For that we use equal to. So let me take same example here to explain this clearly, sir. Now let us take A is equal to 1000 and B is equal to 1000. Now if I say A is equal to B, here I am just comparing their values. I am just comparing their values. So what it will return? It will return true. But now look at this. I say A is B. I am saying whether they are same objects or not. It will return false. Because what is happening? A is referring to 1000 object, B is referring to a different 1000 object. The value comparison, they are same, but they are not same objects. Am I clear? And suppose if I say C is equal to A, and if I say C is equal to A, oh sorry, it should be in the next line. I assigned C to A, that is C also now referring to the same object as A. Now if I say C is equal to A, it says fine. If I say C is A, if I say C is A, then also it says fine. That also fine. See, they are very, very useful with, you know, sequences. For example, if I am having a list 1, say 1, 34, 56.7. Okay, but with floats, sometimes it may do differently. Please note that. I am having list 2, that is 1, 34, 56.7. Now I have two list objects. Now I want to verify whether list 1 is equal to list 2. I want to verify whether list 1 is equal to list 2. So what it will say? True, because their content is same. Their content is same. The values are same. But if I say list 1 is list 2, what it says? Babu, check, because they are not same objects. They are not same objects. Okay. See, what actually may happen here is list 1 is referring to this particular memory or object, list object, which is container of other objects, where this fellow contain address of 1 or reference to 1. Okay. And this fellow may contain reference of, you know, the other one, 34, whatever it is, and 56.7. And list 2 will completely go into a different object. Sometimes these fellows may refer to the same thing. This may happen. This may happen, sir. Okay. If you compare list 1 0 is list 2 0, because this one object is fixed. Because I told you na 0 to 256 is same object. So it may happen. Okay. That may happen. So if you just check that, for example, okay, let me write here itself. Why to write separately 0 and list 2 0, because there one is created only once. See, you see, because both are representing same thing. Both are, you know, from here it is referring to this, from here it is referring to this. Even 34 also may do the same thing, because 0 to 256 the objects are created. See, li1, you see this li1 and li2, li1, li21, even that may return true. But this 56.7, because for float every time a new object is created. But Python generally what it will do, when object is already available, so it try to use the same objects there. So generally even for this it may return true, my dear friends. but here it is creating separate object. Not guaranteed, but 0 to 256 the guarantee is there, because 0 to 256 those objects are created when Python interpreter starts. That is the idea. Is that clear, sir? Like that. So this is or is not is generally used to check whether the two objects are same or not. That is, if they are variables, we try to check whether they are referring to the same object or not. Is A is B means if they are referring to the same object, it returns true, otherwise it returns false. A is not B. If they are not referring to the same object, it returns true, otherwise it returns false. That is the story. Okay. The next one is membership operator. See, membership operators are used to test whether a value is a member of a given container. It may be sequence, dictionary, sequence in the sense list, tuple or anything, dictionary or a set. So now in the previous example, you see 1 is a value. So we want to check whether 1, sometimes within the list you may have variables also. Okay. So you want to check whether that value is present in that particular, is a member of that particular container or not. For that we are going to use this membership operator. That is, we are going to use this in. Okay. For example, a value 1 in li1, true, because it is available, that is a value in that particular container. It returns true if the value is found in the sequence, false otherwise, and not in is reverse of that. If it is not found, then it returns true, found, then it returns false. They are just in, not in, opposite of each other. Let us see the same thing. 1 in, because we already created li1, no, so I am just using. Let us see, 1 is in li1, yes or no? True. 34 in li1, yes. 56.7, huh? I don't know. If you write wrong number, it will say sorry. True. 56.7 only. Yeah. So whether this element is present in that or not, it will verify. So you can also use variables, sir. Instead of this 1, 3, 4, na, you can create variables, and variables can be objects within the container. That also you can verify. So this membership operators check whether the value is present in the given container or not. Okay. Please note, equal to, that is double equal to, check whether the values are equal or not. Identity, that is check whether they are same objects or not. Then membership in, check whether a particular value is present in a container or not. That is the idea. So once you completed all this, we are now at the final step. We try to check the precedence of operators. See, unlike your C programming or any other programming, we don't have to worry too much about this precedence. Normal precedence will be there, sir, because we have some internal restrictions also. For example, you see exponentiation is actually having higher precedence than unary operator, which is generally mentioned as right to left associative, but there is a problem here. Okay, when that unary operator is on the right side, it will be having less bonding. On the left side, it will be having more bonding. So let us try to understand, sir. The power operator binds less tightly than the arithmetic or bitwise unary operators on the right. So on the right side, if you are having this unary operators, that binding is less for power operator. We try to understand this, sir. This is very interesting. So separately, I'll try to take examples and explain. So this is the order, sir. Parenthesis, unary, parenthesis, then exponentiation, unary operator, multiplication, addition, shift operators, bitwise. That is, all are bitwise operators only, but in that bitwise shifts are having more precedence than bitwise and XOR or operators. Then the relational, identity and membership, all these are having equal precedence. Boolean, not is having more precedence than Boolean and Boolean or. So not and or is the order of precedence. Conditional, that is generally ternary operator. See here, you need to be very careful, because the chaining won't happen as you expect in other languages, sir. So you have to be careful. It goes left to right only. Assignment operators. See, we have regular assignment operators or compound assignment operators. We also seen that the compound assignment operators can also be used for bitwise operators together with bitwise operators. So let us try to understand with some examples. So this is the story, sir. Mnemonic someone asked, but I don't think we get a proper mnemonic. PEUMA. Actually, in C language we are having one mnemonic like Pumas Rebel TAC. Okay, but here, so PE exponentiation is extra. PEUMA SB R. So relational. Okay. So in C language the order is like, you know, Pumas Rebel. Okay, RBL, REBL. Okay, TAC. Okay, ternary, assignment and conditional. Okay, that is how it goes. Okay, but here this is the ordering, sir. I don't know, if you want you can try some mnemonic for this. Okay, PE UMA SBR BC. I don't know how you read it. You try to create some mnemonic from this, sir, if you like. Okay, now as I told you, exponentiation. You see, normally exponentiation, when you are having, actually speaking, exponentiation is having higher precedence than the unary minus, but it is not calculated like this, my dear friends. No, this is taken as 2 power minus 1. So on the right side, this power operator binds less tightly. But if you are having minus 2 power 1, in this case, here what happens? The power operator takes first, that is 2 power 1 minus. So the answer would be minus 2 here, whereas here it is not minus 2 as here. So here 2 power minus 1 means 1 by 2. The answer is 0.5. So that is the example which is given in Python documentation itself. Please note that. Am I clear? So this exponentiation on the left, it binds tightly, but on the right side, if you are having unary operator, it binds less tightly. So this minus will be first applied to the number, then finally exponentiation will happen. But if you see the order of precedence, it looks like exponentiation is having higher precedence than unary. But on the right side, unary takes higher precedence, like because it binds less tightly. On the left side, exponentiation is having higher precedence. Please note that. Then multiplication operators, they are all right to left, I mean, except this exponentiation, all are right to left, I mean, all are left to right associations only, my dear friends. All are left to right association. Of course, unary is also generally left to, I mean, right to left association. You can say exponentiation and unary, they are right to left association. Because minus of minus 2 means left to right. How it can go? It can go from right to left only. Minus 2, minus of minus 2. So right to left. Exponentiation and unary are from, you know, right to left. And assignment operation also, because assignment, what happens after expression is evaluated, then the value is applied. But generally they don't take this, the right to left, they will not mention here, because the chaining is not available in assignment operation. In C language, that right to left association is very important. Why? Because in C language, if you are having A plus is equal to B minus is equal to 5, this is allowed in C language. Because of that, you have to say right to left association. But in Python, this is not allowed. Okay, this chaining is not allowed in Python. Okay, obviously, right hand side expression is evaluated, then that is assigned in this order only. In that sense, you can say it is right to left, but that has no real significance to mention. Am I clear? Because whenever such chaining is happening, then you have to mention, okay, whether it is right to left or left to right. Please note that, my dear friends. Okay, you can take some problems here, my dear friends, with precedence of operators. I'll try to come up with some more problems. Okay, please practice them. So I want you to note this very correctly, or this precedence is very important. Exponentiation, of course, parenthesis obviously will have higher precedence always. Parenthesis, exponentiation, unary, multiplication and addition. This is very important, sir. This is very important. Mostly you can expect problems from this. Okay, the shift operators generally they will not combine with other operators, sir. So directly the bitwise, see, bitwise negation is unary operator, so that fellow will go here. Bitwise negation is here, sir. Please note that. Okay, so bitwise negation. Oh, it is unlocked or okay, it's going right. So that is the story, my dear friends. Then comes in the boolean, of course they go together. That is very important point to be noted. And conditional, generally the problems will be separate problems, sir. Okay, so generally whenever they ask questions based on this parenthesis, exponentiation, unary operator, and multiplication and addition operation, based on that the questions they can ask you. Okay, we already solved few problems, you can take few more problems. Suppose you are having like this. What is the order? Because multiplication is having higher precedence, multiplication operators means we generally call this fellow, and these fellows. That is, these four fellows are called multiplication operators. So multiplication operators are done first from left to right. So first this is performed, then this is performed. So what happens here, sir? So it is 5 plus 2, floor division 3. So what is the result, sir? 3, 2 zeros. Okay, 0, 2. So what is the answer? Floor division is 0, because 0 point something, still the answer is 0 only. So this answer is 0. 7 percentile 8. So when you divide 7 with 8, 7 is the remainder. So 7 is the remainder. So the answer for this would be, then of course this will happen from left to right. 5 plus 0 is 5. 5 minus 7 is minus 2. So if you take this particular value, you can check the answer, that is 5, minus 2 is the answer. So let me just take this and verify. I randomly taken the number, sir. You can check the answer. The answer is minus 2. Okay. If you understand, you can always create any problem, sir. Even exponentiation, you have to be very careful. With exponentiation, just now I told you, exponentiation also we can check that. Okay, 2 percentile minus 1. So the answer is what, sir? 0.5. It is like 2 power minus 1. So actually exponentiation, you may feel like it is having higher precedence than minus 1. So people say like 2 power 1 whole power minus 1. It is not like that. Okay, on the left side, for example, if the exponentiation is, this minus sign on the left side, here what happens? 2 power 4 with a minus sign. 2 power 4 means what? 16 with a minus sign. Minus 16. Please note that. Okay, so we can just make some other expressions. Now it is right to left associative. Okay, exponentiation is right to left associative. So first 4 power minus 2. What is 4 power minus 2, sir? 1 by 4 square. 1 by 16. That 1 by 16 to the raise 2 power 1 by 16. It's like 2 power 1 by 16 with a minus sign. So I don't know 2 power 1 by 16 how much, I do not know. Okay, so that would be the answer. So like 2 power 1 by 16, you can just verify. You can directly check that 2 power 1 by 16. You can check, that would be the answer. Same. This is the answer, because 16 with 4 power minus 2, that is 1 by 16. Am I clear? That is what happens. Please note that. Okay, so that is about your precedence of operators, my dear friends. Okay, we can come up with more and more examples, sir. Regularly we will try to take up, because problems on this would be very, very important. So this is your precedence of operators. Please note that parentheses are having higher precedence than exponentiation. Then we are having unary operators followed by multiplication and addition, shift operators. Then we are having binary. Okay, then after binary we are having relational operators, identity and membership operators, then boolean operators. Of course this is bitwise. There are two bitwise, bitwise, boolean operators, that is boolean, and actually logical operators also people call. So let us call it as logical operators. Let us call it as logical is the better name for this. So let us call this, instead of boolean, let us call it as logical operators. After relational, logical operators, conditional, and finally assignment. So this is the order, my dear friends. I suggest you to call it as, sorry, because that is a printed one, I cannot change it. But instead of calling boolean, let us call it as logical, so that 2 times b will not get confusion. So this is the order, my dear friends. This is the precedence order. Okay, we'll try to take, yeah, KV sir. Oh, very good, Swami sir, super, perfecto. So that is about your precedence of operators. Am I clear? So what I do is I'll try to give you some questions. Okay, maybe within the chat box you can find out some questions. Okay, try to answer those questions, my dear friends. Okay, and next class tomorrow we try to start with the conditional operators. Control flow structures. Okay, so that's all for today. If you have any doubts, you can ask me. Otherwise, we'll call it a day.